Thanks, Amitha, and thanks to the organizers for inviting me today to give this talk, and also for rearranging my schedule. I got drafted to go to jury duty tomorrow, so I couldn't make it to present tomorrow. So my talk today is dealing with this concept of design of cyber-physical autonomous mobility platforms. It's a little bit different from the previous talk, although it's the idea is talking about autonomous vehicles, but I wanted to focus on another dimension, which is looking at the platform design aspect and looking at mobility as a service. Right. So as we know, the transportation field has changed significantly in the last few decades, where once it was dealing primarily with developing highways and transit routes for transit networks for mobility. Now there's a lot more of different roles that decision makers and operators can play in producing what is called a mobility as a service. Right. So here are some examples where you see like the Federal Transit Administration has been running this mobility on demand sandbox, and you can see that some states like California have been trying to develop integrated transportation systems platforms to facilitate travel for, in a unified manner. Right. So this is what we're seeing today, and at the same time, we're seeing this way of defining how mobility works to this more of a mobility as a service type of ecosystem, right? So a common definition that has been used more recently is that mobility as a service combines transport services from public and private transport providers through a unified gateway, right? And it's trying to create, using that gateway to manage trips for users through a single account, right? So the idea is that travelers are now interfacing with not just one mobility operator, but it could be multiple mobility operators, and typically through this third party, that this platform that's managing the travel. Here on the right-hand side of the screen, you can see different types of governance styles that we're starting to see emerging, right? Where the governance style A is the more of the conventional approach of government working with suppliers to provide services for travel. But now we're also seeing ways that government can act to act towards a broker, being a broker, an aggregator, as well as establishing new relationships with suppliers. So this is all happening pretty quickly in the last few years. And along with this trend that we're seeing, we're also seeing this trend of autonomous vehicles. And that's primarily, I think, one of the main topics that the audience here is here for today, right? So looking at autonomous vehicles, we're also seeing a lot of development along the shared or connected autonomous vehicle fleets. These are just some of the deployments, and actually, these are even maybe 2 years old, so there's more recent developments since then. Okay, so these two trends, when they merge together, they raise a couple of research questions that my research group, the Build Lab at NYU, has been tackling these recent years. One of them is looking at how do we evaluate the stability of an ecosystem of these kind of mobility providers, right? When a new service enters the market, or if a new service changes or improves their technology, like the routing algorithms, the matching algorithms, and so forth, what is the impact on the market? Two, how can public agencies facilitate these kinds of ecosystems, right? So how can we provide the tools to public agencies to let them evaluate various interventions? And these interventions can relate to infrastructure investments, subsidies, pricing policies, taxes, regulating the market in ways toward that kind of a system optimal setting. And of course, the question of how automation might affect these systems. So to tackle those questions, I'm primarily approaching this from the mobility as a service market perspective. This outline, as you can see, I will talk about platform economics to kind of introduce the audience to those concepts, and then we'll go through the market evaluation modeling of these cyber-physical platforms. And towards the end, I'll comment on some of the other works that we've been doing towards automation and how that can impact these mobility as a service markets in the near future. Okay. So the topic that we're dealing with here is looking at these systems, these markets that operate as essentially multi-sided platforms, right? So we're very familiar now with the sharing economy and how there's been many types of digital platforms that have risen in recent years to provide to facilitate transactions between two or more parties, right? It could be buyers and sellers, and examples might be Airbnb, Uber, Lyft, and so forth. I post definition provided by Rocher and Thoreau from 2006, right, where they say multi-sided markets are markets in which one of several platforms enable interactions between end users, sorry for the typo, and they try to get the two sides to be on board, right, to host these transactions between them by appropriately managing and charging the different sides. All right. How does the mobility marketplace mimic this type of platform? Right, so we can argue that cities are essentially multi-sided cyber-physical platforms themselves, right? Because in a way, cities, the way that they're managed, they're looking to try to connect the travelers with mobility services, right? So that in this case, the travelers are the buyers, the mobility operators are the sellers. The platform in this case is cyber-physical in the sense that the cities are managing the costs of these transactions towards the two parties, either physically by making changes to the built environment, right? It could be changes to the road infrastructure, adding new infrastructure, changing the way that it's controlled, or it could be digitally by using travel information, travel apps to manage trips between travelers and operators, or allowing them to match online, as well as e-commerce, like from the perspective of goods delivery as well. In this sense, if we look at cities as multi-sided cyber-physical platforms, they are essentially doing this platform pricing using the combination of these tools, right? These policy tools, looking at controlling the built environments to augment the travel costs, which become those transaction fees between the travelers and the operators, or looking at controlling the taxes or subsidies to incentivize travelers and operators to participate in this market, and also do those regulations, which can also augment the pricing structures that impact the travelers and operators. Right, so on the left-hand side, you can see an example of how this breaks down into this looking at public agencies, in this case, in a city context, and how they are providing this platform in a cyber-physical format towards operators and travelers. And when we look at it from that perspective, it really provides us with ways to consider different models to evaluate mobility as a service as this kind of platform, right? So we can borrow a lot of the platform economics concepts to play and to allow us to evaluate these various use cases. So here is just a breakdown of some example use cases, some drawn from the previous slide, but just to provide the context of how the tools, if we have the appropriate tools, it can really broaden the scope of what we can, how we can help these cities manage these MaaS platforms for different travelers and operators. Okay. So, so the question now is then how do we provide such a model that can actually handle these types of different designs, right? How do we have a model that can evaluate different platform designs that can accommodate changes in the system in terms of operators participating in the market, as well as users traveling in the market in a multimodal fashion or intermodal fashion, and still allow us to quantify those changes for the evaluation of the whole market. Right, so the next couple of slides primarily are drawn from the first paper that you see listed here, and some of which also come from the second paper. So the motivation here is now when we look at a transportation network, right, and here you can see an example of one. The change in the way that we look at this is that it's no longer a network that's just managed by one operator. So when we consider flow, that let's say there's flow going from node 1 to node 3, and there's flow from node 1 to node 4, but the paths that go that can take travelers from those nodes to the other nodes are divided and owned by multiple operators, right? So, for example, travelers from node 1 might go directly along a path from 1 to 3, or they might via a blue operator, or they might take a path from 1 to 3 by stopping at node 2 via the blue operator and then transferring to an orange operator to go to node 3, right? And so when the blue operator is deciding, they're making a couple of decisions, right? They're deciding whether or not to provide service along those routes. They're also deciding on what kind of cost allocations for example, what fares to charge to charge. They have to make these decisions system-wide, taking into account that they are both competing and potentially cooperating with other operators in the market, right? We also want to have a model that can allow us to evaluate these networks where there are potentially capacity effects or congestion effects, right? So like the fact that a certain route can only fit up to 2,000 travelers. And so the demand would have to end up shifting to other alternative paths. So we're, in essence, we're trying to take conventional traffic assignment models and incorporate multi-operator setting into that kind of problem, right? Yeah. So
So, quick question:
sure.
Is the operator allowed to? Is the capacity a control as well here, or is the capacity fixed?
So in this setting, the capacity is fixed, but we can then look at the case later on where, let's say, a scenario has changed where the operator has the funding source to expand upon the link capacity. But for now, we're saying link capacities are fixed and operators are deciding which links to serve. Okay.
Thank you.
Okay, so to look at this kind of model, we want to start by setting some assumptions, right? So here we do assume that the travel utility from travelers are transferable with operators in some way, right? So for example, transit operators' performance, they may or may include travelers' disutilities like wait time, right? And that's very common for public operators. Shared rides or detours might facilitate discounts in the fare pricing, increase access time, perhaps because the operators might have algorithms that ask travelers to make to access to virtual stops as opposed to just picking them up directly, and in exchange allowing travelers to get discounts or looking at transfers, right? So all of these are ways that in one way or another, transfer utility back and forth between the operators and the users, the travelers. And we're also making the assumption that operators, for now, they charge a single access constant fare. So basically, if you're using a certain operator you pay a fare to them, and if they have multiple links, you're still just paying that one fare to make use of that one operator. All right. So based on these two assumptions, we can put together a model to evaluate this kind of marketplace. All right. So when we consider that utility is transferable, we can make use of transferable utility games. And so when we look at those kind of games, those are called assignment games. And assignment games are basically games that are set up to have essentially like two subproblems, right? Where you're matching buyers with sellers to generate as much utility as you can. And you're also ensuring that that matching is stable, right? So there's a subproblem there where you're trying to optimize the matching between the buyers and the sellers so that they maximize their profit. And there's also, given that optimal matching, you are identifying the space of stable outcomes that would be able to facilitate that that matching, right? That stable outcome subproblem can end up having multiple solutions, of course. But even with multiple solutions, it's possible that you can end up having a stable mechanism within that space that can be best suited for the buyers, right, the travelers, or it could be one that's best suited for the sellers or the operators. And we call those the buyer optimal and seller optimal vertices of the stable outcome space. And so a key part of this is basically we're trying to optimize the assignment of travelers in this operator-owned network and ensuring that that assignment is stable by identifying the space in which the incentives are there for the travelers as well as all the operators. If the stable outcome space turns out to be empty, which could also be possible, it suggests that the assignment, that optimal assignment, is not a sustainable assignment, right? And we can also use this kind of model in an ex post fashion, given data of a certain operation. If we're able to identify the stable outcome space for that operation setting, we can see whether or not based on the cost allocation that that operator or platform is running, whether that is stable or not. Right? It would be stable if it falls within that stable outcome space. All right, so just to quickly review, the one-to-one assignment based on the terminology that I introduced earlier would look something like this, which is a simple assignment model, making sure that we match every user to an operator. And that's a one-to-one assignment game, right? And there are stability conditions, feasibility conditions, as well as stability conditions that we can define to ensure that the values that they get for the operators as well as for both the buyers and the sellers are sustainable or stable, okay? So this is for a one-to-one assignment game, which is very a simple case. In the mobility as a service platform, there are complications, right? So in this kind of setting, now we have multiple operators that might own different links in the network, right? Links here actually represent OD pairs. So it could be like getting someone from downtown Brooklyn over to like a major station by taking like a ferry, right? So it's not just looking at street. It's not looking at infrastructure link. This is looking at OD level link. And then you also have, so you have operators that can own different links in this network. And you're essentially matching the users first to user paths, because users have to decide which paths they take. And a path that they take can end up connecting with multiple operators. Right, and so you're matching users to user paths, and then user paths are being matched to operators along those links. And so this kind of matching setting becomes a many-to-many assignment game. All right, so the many assignment game is problematic because there are the uniqueness of the solution, at least in terms of the paths, is not guaranteed. But at least there are other insights you can draw from it, which we'll discuss later. All right. There's also the fact that this type of system, we have link capacities that lead to these network effects that have costs to binding capacities that impact the routes that people choose to take. Right, so we want to take that into account as well. And the matching subproblem itself ends up becoming this multi-commodity capacitated network design problem, which is a very complex model to solve, right? So just some notation to introduce to this more complex setting, right? So we have travelers that are making trips. Each link that they're traveling has a disutility, generalized disutility. There's also a cost that is incurred to the operators for operating a certain link. There's demand at a group level, right? So for different OD pairs, those are the S. The user groups, there's demand, and there's also capacity flow along each of those links. So in both the matching subproblem and the stable outcome subproblem, we have a number of variables. So the decision variables in the matching problem include the flow of the user groups, as well as binary variables of which links that should be operated to obtain the most to obtain an optimal flow assignment. And given that those optimal values, we can take those values, and then in the stable outcome subproblem, we're also deciding what prices operators should charge to travelers, and where we also have to convert the flows of the user groups over to path flows that are matched with operators. So this kind of assignment game can look something like this, where we have the matching subproblem. The matching subproblem on the left-hand side is essentially a multi-commodity capacitated network design problem. And on the right-hand side, we have the stability conditions as well as the feasibility conditions to ensure that when there is a matching, that the costs incurred, that basically given a certain price that operators would charge the users, the PRF, is set so that they have incentive to operate their routes, right? So the operators have the incentive, as well as the users have the incentive to traverse those routes. And note that on this right-hand side, we're using the path flows and the binary variables that have been identified in the left-hand side to use those in the stable outcome subproblem. All right, so in this kind of model, we can then identify a set of flows that are optimal for multiple operators, and we can also determine potential stable outcome space that could fit that solution, right? And if that stable outcome space is empty, then that solution is not likely not to have a stable outcome. If for this kind of model, it also points out that we need to enumerate alternative paths as a base case, right? Because we actually have to determine for a given path that travelers are using, if they have to divert to another path, what would be the trade-off costs? And so in the base solution approach, you might need to enumerate alternative paths. So keep that in mind, because one of the things that we try to do is to avoid the path enumeration, right? So the model itself leads to this non-unique setting, but there are certain properties that can be gleaned from such a model, right? So we know that link flows and total path costs, they are unique. And so like the total revenues and the total consumer surplus, we can get unique values from there. And even if we have a unique stable outcome space for a given matching, even if we cannot get the reverse to happen. And the model can be also used in an ex post evaluation, where if we have an operation already that has taken place, we can evaluate whether or not it's stable. And from there, provide suggestions. We can apply the model in a simplified setting to analyze stylized examples. So one simple example might be looking at whether or not an orange operator might choose to cooperate with a blue operator, or if they should compete with them to serve customers. And we can derive closed form expressions to represent the conditions where they can set the prices for that. And similarly, we can also look at the case where there might be travel along a corridor, and an orange operator is deciding whether or not to enter a market to provide service for a sub network for travel for travelers. And again, we can also, in those cases, we can derive the conditions to obtain those optimal prices. And this is for these stylized cases. But for more complex cases, we have to deal with that path enumeration approach. So what we proposed in the paper from 2020 with Pantelidis is to use this approach of...
Sorry, Joe, quick question.
Sure.
Hani has a question. He would like to see whether you could comment on the assumptions that would guarantee uniqueness. So for under complex interactions, uniqueness is typically unlikely.
Yes, that's true. So the uniqueness of the path flows are not. So that was the previous slide where I was saying that uniqueness is not guaranteed for the path flows. But for the link flows, and when you look at the total path costs, and because of that, you can ascertain the total revenues and the total consumer surpluses along those. So should I continue?
Yeah, just also very quick question I have as well in the previous slide. So you said that you can sort of in closed form answer when you need, when certain situations occur, when there would be collaboration or competition.
Yeah.
So what is, you say if only if its price can be charged is higher than something. So what is constraining the price? Why can't you charge a price that's higher than that?
So the trade-off there might be that they might not want to, if this is also looking at user benefits as well. So the user might want to have more user optimal case. So if it's completely private, then of course they would just maximize the price.
Okay, so you're assuming a setting in which the operator is profit maximizing under user constraint.
We're looking
demand function.
This is so we're looking at the set of all stable outcomes. So it could be that they're profit maximizing, in which case they would try to strive towards a seller optimal outcome, or it could be also one that's more public setting that they want to make it more buyer optimal. So in that case, it might make sense for them to want to set a lower price. Okay.
Thank you.
Yep. So in terms of an algorithm to try to address the essentially generating constraints to avoid the explicit path enumeration, we borrowed an approach that was developed for shortest path games, in which you're trying to solve a shortest path assignment problem where you each link is a distinct decision maker, distinct operator. And the way that they do that is to define a set of permutations of different orders of coalitions between the sub-coalitions between the operators on those paths. And they would iteratively remove those sequences to generate, essentially what's generated are the paths along the frontier. So you don't have to actually generate all the other paths. You just generate the alternative best paths that you would compare against. So by doing that, we can make a significant savings against trying to actually enumerate the paths explicitly. So going back to that numerical example, just check on time. Yeah, just going back on the numerical example, we can show that this can generate flows as you see on the green arrows, which would result in a splitting of the operator. So the top groups are like on the left is the operator A, C, D, and then the routes are on the right hand of that. So like the first row is operator A, user route going along 1, 3, and you can see the flows are along each of the paths and the prices that can be charged either along the buyer optimal or the seller optimal vertices of the optimal of the stable outcome space. We expand this to larger cases, or at least some more realistic network examples, and show a variety of different scenarios that can be evaluated, right? Looking at the case where, let's say you have 2 private operators and one of them gets overtaken by a public entity. And so in that case, the public entity changes the objective to be more buyer optimal, looking at changes in capacity, look at technology changes that would result in changes in either travel disutility or operating costs, or looking at the case where a new operator joins the market and how that would impact the existing market. And we also try looking at how well the algorithm can scale. So I'm not going to go into the details of this. What we can summarize is that the algorithm can solve of those simple examples sufficiently well. The base scenario also, we are able to show that even if government, there under certain conditions when the government rail acquisition takes place, it still cannot really benefit the users because of the nature of the way the trips are being shared with private operators. So like if the public operator is sharing those routes and they end up conceding some of the benefit over, that benefit would get cannibalized by the private operators. New competitors can result in significant advantages to a third party, and capacity increases can have we can see nonlinear effects. So that's also interesting to observe. We've tested this also, or at least the main framework. This was not in a multimodal setting, looking at applying this to a microtransit service in Luxembourg. And you can see on the right-hand side, there's a graph. The graph here illustrates the ticket price of for the service. The blue line on the furthest on the left of that graph, that was how the Cusbus microtransit service was operating. And the red and yellow define the stable outcome space that this service should have had. So we we showed that operation that they had was not really sustainable, and in fact they ended up closing down shortly afterwards. Right now we're also our group is working with New York State DOT on their next statewide mobility service program, and we're considering some alternative extensions to this work. Let me just quickly go over some of the points about automation, how this can impact. So we've done a number of other studies as well on how automated vehicles in a fleet setting can benefit through benefit the operations. One of the ideas is trying to incorporate more optimal learning so that there's more explicit exploration of the fleets. So we've done tests to illustrate that, both for just route selection as well as for planning out routes in a more sequential manner for these autonomous vehicle fleets over time. We've also looked at how if autonomous vehicles can self-valet, it can help introduce these new fractional ownership business models where a fleet of vehicles might be owned by various users, almost like a timeshare type of plan, where you would just own slots of time, and you can trade that with others. And so like this is an illustration where we were able to price out the time of day prices for different time slots for a set of vehicles that might serve commuters in the Upper West Side in New York City. We've also looked at how with autonomous vehicles, we might be able to look at modularity a little bit better. Vehicles that can join together to create larger size vehicles, because now you're not having to deal with drivers in the systems. And so dispatch can be more dynamic using stochastic optimization. And we can also see that transfers can be reduced because travelers can get onto vehicles and transfer on route. And some of our experiments have shown that it can reduce travel distance and wait time for some examples. So just to conclude, mobility as service markets, they need to be evaluated as these platforms, and the design of such platforms can be evaluated using these many-to-many assignment games. And so we are applying this we're looking to apply this more to like realistic networks to derive important insights. For example, we've done some with Kusbus in Luxembourg, but we're really interested in looking at multimodal system as a next case. And in terms of automation, we think that there's a couple of ways that autonomous vehicle fleets can benefit in terms of optimal learning, self-valets, and modularity. Okay, and that concludes the talk. You can reach me at my email address here or through LinkedIn. And these are some of the researchers whose work I mentioned in this study, in this presentation. All right, thank you very much.